Right. So this, out of like all the topics in CS 121 and 122, this is probably the most important topic. Like aside from polymorphism, but polymorphism is like an idea. This is like a thing you can do. So recursion is like a very old concept as far as computer science goes. Even though computer science is not old itself, this goes way back. So originally, lots of languages didn't have like for loops and while loops. For example, the first object-oriented language, Smalltalk, didn't have for loops, while loops, any type of loops. You had to do all looping with recursion. So we're going to talk about how to do recursion and just how it works, and just pick one of them that you can kind of wrap your head around and try to develop an understanding of it. Some of them might seem like a little bit weird, but if they do, then just find one that you frame accepts. But in the beginning, we'll do a very easy one, so that it's kind of obvious how it works. Okay, so let's do recursive thinking. And just so that you're aware, I haven't gotten it out yet, and if you did beat me to it, I would really not have a problem, but I am planning on getting it out if it's sticking around a few more days. There's a book in the library, Recursive Thinking by, well, there's only one book called that, and it's like the classic work about recursion. Yeah, so it's all about recursion. So if you are interested in learning it, they do have that in the library. And as far as the computer science section goes, they have all of the classic textbooks. So go to the Q section, hang a left, you find it. So recursion essentially just means a method calling itself. That's it. So you probably already considered what recursion is. So we'll do the next couple of slides, which are descriptive, but let's just look at what recursion is all by itself. We'll just make a method, we'll have it call itself, and then we'll see what the problem is when it calls itself, without us changing that at all. And we'll say how recursion is used to actually do effective loops. Okay, so we got our program here, and just to make it more easy, we'll just stick the method inside of the class, which, like in other languages like C, etc., it's very common to have methods attached to the driver program, but in Java it is less common, but you're allowed to do it. So we can just say, as long as you're within the last curly brace, not inside the main, but within the curly brace of the class, put a method in. And it's got to be static. So we'll say, let's make it a string. And no, let's make it. Okay, so here. Okay, so right now it doesn't really do anything. It doesn't even call itself. So if this was a recursive method, the first part would be that it has to have a line that says call itself. So it's going to just say recur one and pass itself in its string. notice that you're allowed to do that. We're satisfying the method. We're passing it an integer. So we can run this, and we'll see that it will just loop over and over again. But let's put a print method in the main so that we can see that it's actually doing something. Let's just have main say print line, and then give this an integer, and then all it's going to do is return 1 anyway. So it'll give us back a 1, so we should see a 1 when we print it. Just give it a 5, we'll get back a 1. Okay, so we're giving it a 5 to satisfy the integer. We could have made it a void parameter list, but we'll make it do something in a second. So right now it says it calls itself by passing it 2, which also doesn't really do anything. The only thing that does anything is return 1 is going to give 1 back to the print statement. So we'll be able to see that. And it should also crash the memory. I don't know how long it will take because this isn't very memory intensive, but if we made a more intensive one, it would crash the memory sheet a little bit. Let's try it. I have to call them out. You may have sensed me go into temporary panic when it didn't do what I wanted, but don't worry. It will do what we want as soon as we call the method. Past the method recur 1. So, well, I guess it threw the 1s out faster than we can see them, which is not fun. But it did a stack overflow. This is clearly that it did do the print because you don't see a stack overflow unless it actually ran. So a stack overflow means the memory flooding, and that's because of all the recursive calls. When you do a method call, it's much more memory intensive than just like printing out one. So this is recursion. Let's try to do something where we try to tell it to stop. So let's say it's past it, recur to, and anybody have an easy way that we could just playing around with this, make it do something and then stop. At least so while we're calling the method by itself. So like we can use a break statement. So let's say
A while loop maybe, or for loop?
well, we're using recursion too because we're not using while or for loops. We're imitating a while loop or for loop with recursion. We can use an if, we can use a if else, but not while or for, because we're attempting to imitate them with recursion. So let's see. Let's try something where we'll make a local variable. Actually, let's make it a moving variable. Easier to do. I'm just testing that it's visible in the method. I was expecting it would be, but I'll make sure. So let's say x plus 1. So let's say if x equals 5, x equals 5, return. Okay, so let's see what it does. I'm not even sure exactly what it's going to do, but it's going to do something along the lines of this. The reason I'm not sure, what it's exactly going to do is that I'm not thinking about it. I want to encourage you just to finagle with your program and kind of expect a certain thing, like we say, when x is 5, then return 3. So we may or may not see it frequently, but if x isn't 5 and it starts out at 0, we set it at 0, recur x plus 1. So that means 0 plus 1, so it is going to be 1, then it's going to be 2. Also, let me change this to a static. It should have a, it's interesting, because usually they want you to use static variables inside of this. Okay, so we're adding a 1 to x, and then we're saying return 1 at each point, and it's adding 1 to x so that it can return back to where it was called from, so we can see if we're going to get a printout from that, and we'll get the 1. Mainly we want to see something without the static overflow. So we're calling recur 1 at some point. If you're ever calling a method name that is a method itself, this is recursion in some way. But right now we're just attempting to make it so that we're not going to have it keep going. We want to make it stop a little bit. I was going to try break, but break is for when you have a loop, a real loop. So even though this is a loop, it's not going to recognize that it's a loop, so break won't be as loop. So we've got 3. Okay, so now, if you're wondering why we don't see the rest and it just says return 3, what has happened is the following. We're going to add a couple more print statements. And this is the part about recursion that we'll discuss and then talk about during an example and discuss again. What recursion does is that it does everything until it says if x is 5, then return 3, and then the program's over. Because that is how recursive algorithms are designed to go. They're designed to go like if a while loop said while x does not equal 5, then do the while loop. So that when x is 5, it'll stop. With recursion, you usually give it a place where you say, at the time that the variable equals this thing, then stop. So there's usually 2 return statements in a recursive algorithm. So what this did was it passed the 5 here, and actually I didn't even notice that we were using x. So you know what, let me change this to something else, but it's not going to change our outcome very much. Let me change this to in, because being that they were both x, that would have confused between the local and the global. And also, let me just pass this a 1 instead. So you got oh, I see. Okay. All right, we'll go back to the x here. Let me just quickly try and fix it. Just test what I need. So, hang on if you're not totally getting what's going on. So let's put the return statement for this one inside of the curly brace so that I can put the return statement before it. X. Okay, so we're sending it down 1. It's going to do x plus 1, but it's going to print the value of x the first time it goes through. So now we should see at least something. And if we don't, I'll stop the program from crashing before we do. But then at some point, when x is 5, then return 3 and the program's over. So x starts out as not 5. So every time that the method calls itself. It goes back up there, and then it says, is X 5? If it is, then return 3, and then it's over. It doesn't go through here. So it only does return 3 when X is 5. When X is not 5, it does the bottom one. So let's do this again, and also we'll look for what these printouts are going to come out as. Okay, so notice we got 4, 3, 2, 1, 1. So now you're probably thinking like, this is really weird because I gave it a 1, it starts out at 4, so now here's part of our recursion you gotta understand. The recursive methodology does all of the passes to it until the final situation is met, like when X is 5. But then it saves all the previous answers, like, you know, it does the first one, passes it a 1, recur X plus 1, and then it does all the printouts, but it like saves them off on the side, like written down. And then when it gives you the answers, it gives them in reverse order. It says, here's the one that came out last, just as this case was met. Here's the one that came out second to last. Here's the one that came out third to last. Here's the one that came out right before that one. Here's the one that came out right before that one. So recursive methods show how computers use something called stack. So there's a stack in chapter 13 that we're going to do, but there's also a stack in computer architecture that is mean. So notice here we've got this as an output. So it's because it started out here. And let's see if we can do. So we have x equals 5, x. Okay, so the reason I wanted to build it this way was to show how first when we built it, it just looped, and then when we built it second, it was fed a variable and then it was able to call itself until this was met. And then when x is 5, return 3. So notice we don't see a 5 here, because when x is 5, there is no print statement, and then it says return 3. So we can find out why we didn't see the 3 there. But the point is that it starts out by giving it the first one, and then the second round through, the third round through, the fourth round through. Then when this is met, the stack inside the computer says, all right, so the last one that we computed is this one. Here it is. The next one that we computed right before the last one is this one. The one we computed right before that is this one. So if you do a loop, like say if you do a loop to add up all the numbers from 1 through 10, you would see 1, and then you would see 1 plus 2 is 3, and then you would see 3 plus 1 is 4, and then you would see 4 plus 1 is 5, etc. Meaning if you were to add 1 to them all the way, you know, from 1 to 10. Or if you added all the numbers 1 to 10, meaning add 1 to the number 2, you would get 1 plus 2 is 3. If you added 3 to 3, you get 6. If you add 3 to 3, you get 6. And then if you added 6 to 4, you would get 10. So yeah, I think that's the first example. Yes, so let's stick with that one. We'll do the numbers adding up each individual integer from 1 to 4. So we'll see that they're going to come out in reverse order. So say if you wanted to add up 1, 2, 3. If we were adding them up in our normal everyday life, we would say 1 plus 2 is 3, 3 plus 3 is 6, and 6 plus 1 is 8. But the compiler is going to do it in well, let's just do that. Let's see how the answer actually comes out when we do this. So adding up the first 3 integers, how are we going to do that? Let's go and see if there's anything we need to say about this. Okay, so the reason I skipped the beginning part was that a lot of the discussion about recursion is not exactly helpful because it isn't precisely as it is described here. Like it says, a recursive definition is one where it's used to define itself. Like if somebody said, what does green look like? You know, if you try to describe green to somebody who has, you know, who's been born without vision, you know, green is like a pine tree. You're like, what is a pine tree like? It's impossible to use a word to define itself without being undescriptive. You know, so that's kind of the way that it's tried to be discussed, but really recursion simply is a method that calls itself. That is all recursion means, but it's going to mean a lot more, meaning that you have to understand how the algorithms work. So we start out with the real basic ones, and we'll do the add up, the numbers from 1 to n. So like decoration, something used to decorate a room. So that's not helpful. Something that is used to give the room more interesting flavor. That's not recursive, which would be non-recursion is a loop, a while loop or a for loop. But recursion is a method called itself. Okay, so this thing called the base case is where we had that when x is 5. Base case just means whenever you tell the recursive methods to stop calling themselves. Otherwise, it would be looping forever. Just like if you did a while loop and you said, you know, while x is less than 5, and then you made x decrement down instead of incrementing. If you said while x is less than 5, keep doing all this stuff. And then inside of your algorithm, you said x minus plus instead of x plus plus. It would just keep getting away from 5. It would never end. So the base case is the place where you tell the recursive calls to stop happening. So let's look at the sum algorithm to get an idea of how this works. Is there anything we need to really say here? Okay, so recall, as soon as the recursive method calls itself, control returns to itself. So it's kind of obvious, but when it's done being called, the method itself gains control again because it called itself. So those two places where there are two return statements are how you break down the recursive algorithm. Okay, so this part is not overly super important, but you're going to need to understand this stuff for like CS241. You have to know by looking at that, it means sum the numbers from I to n. And then I is the number that you start with, and n is the number that you end with. So we're going to be doing the sum of so that means sum up the numbers from 1 to 4. All the rest story about, but that part, get familiar with the large Greek S for sum. So for our first example, we're going to use this algorithm. So this is like the other thing that you'll pick up in CS 122 is how to write the algorithm out. So this is the actual Java, which we'll see inside the program. But then I think there is a math slide somewhere here. Oh, there will be factorial. Yeah, so we'll see that. So, righty. Okay, so here is the algorithm it's going to have. So it's going to pass it an integer. So say we pass it 4. So sum the numbers up from 1 to 4. So it's going to say when n is 1, then say it's done. It's going to take whatever number that you have and then go down to 1 until 1 is reached and then stop. In this case, whether n was 1 or 0 wouldn't matter. And a lot of times you can use either or, but if it's a multiplication, obviously you can't, because then times 0 would be nothing. But here, if we had n equals 0, it wouldn't change the answer. So that's called the base case. So instead of going up, you usually have your recursive algorithm decrement. You usually have a minus situation, so that the base case is always a 0 or a 1, not some other higher number up that you arbitrarily pick. You just tell the user that the algorithm can do this, and then it decrements down to a 1 or 0. And now, so this is a part where you start just like, first just accept it at face value, because you'll see that it will work. And then we can put in some print statements to show how it works in each step. So notice here this says we have a local variable result. And it says result equals n plus sum of n minus 1. So it looks, kind of weird. If it looks totally clear to you, then pretend I didn't say that, and it's great. For me, it took just forever to understand recursion. It just happens one day, or you're fine with it, it doesn't bother you anymore. But this is going to take 4, it's going to take 4 minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1. So it's going to add up all the numbers until n is 1, then it's going to stop and give you the sum back. So at first we're going to just see the answer unless I did the one that has the print statement in it, so we can see the steps.
So when you get the sum, why is it like sum like n minus 1?
We get the sum, it'll be 10.
Okay, but why is it like n minus 1 there instead of just n?
Because it's got to decrement the number down so that someday it reaches 1, or else it won't reach the base case. Okay, so this is a description of what we would see at some point. So, as I was saying, it does all of the steps, but it saves them and then gives them back in reverse order. So we see that when we give it sum of 4, like we call the method sum, and we say sum 4. So it's going to do sum of 4, sum of 3, sum of 2, sum of 1. And then when it reaches the base case, it's going to start giving the actual answers out, meaning what is the value result equal. So it's going to say result, result 1, result 3, result 6, result 10. So we should see the answers in that order. So notice sum of 4, sum of 3, sum of 2, sum of 1. So we would see the method calls going in proper order, but we would not see the answer in reverse order because of the stack. So the stack is this. So I'm going to write this out with a marker so that you understand why the answers will come out in reverse. Okay, so at first it's going to say sum of 4. So sum of 4 equals sum of 3, sum of 3 plus 4, I think. And then sum of 3 equals sum of 2 plus 3. Hopefully I'm writing this well. 2 equals sum of 1 plus 2. Sum of 1 equals 1. Okay,
So are those factorials there? Like when we said sum of 3 and sum of 2, are those like?
do you honestly think they're factorials?
No, what I meant was like you do 3 plus 2 plus 1 and then you add to 4, right? Is that what it means?
Well, is that a factorial?
No.
So notice that it does the call sum of 4. So in order to calculate the answer, notice that the way that the compiler wants to do this is it says it has to do it by doing sum of 3 plus 4. But sum of 3 doesn't have a value yet. So we go to sum of 3 to see if it has a value, because eventually the one below will have a value. So sum of 3 is sum of 2 plus 3. So 3 and 4 are real numbers, but sum of 2 does not have a value yet. So it can't do the calculation. So it writes those off on the side, just like we have here. And then sum of 2 is sum of 1 plus 2. So sum of 1, we look down and sum of 1 is going to have a value. So sum of 1 is 1. Sum of 2 is sum of 1 plus 2. So 1 plus 2 is 3. So now sum of 2 is 3. So then sum of 2 plus 3 is 6. And then sum of 3, which is 6 plus 4 is 10. So this is how the computer does it inside in the software, like the actual software stack architecture. It does sum of 4, sum of 3, sum of 2, sum of 1. It finally has an answer that it can actually give back. So it gives back the answer, but this one needs an answer. So it says 1, 2, 3, 3, 3 plus 3 is 6, 6 plus 4 is 10. So we're going to see 1, 3, 6, 10, which is not intuitive, but that's how the computer sees it. We'll see 4, 3, 2, 1, 1, 3, 6, 10. Okay, so it's, so let's go to, I think I have here's a picture of what I just drew. So I drew it because you might look at this and it might not make much sense at all, but this is exactly what we drew. So now it should make more sense, since we did it one step at a time. Okay, so every recursive function works this way. So like if this was a loop, every time you do a loop, you see everything in every step of the loop. But with a recursive function, you only see the answer at the end, because remember, methods receive the flow of control from the method that called in. So a recursive method has control through the whole way. So the return never goes back to main until it's all done. The first time that the method is called, it's passed an integer. But then main, you don't see main in action until the end, because we give it the integer, we say sum of 4, and then it takes 4 to 3, 3 to 2, 2 to 1. But main has nothing to do with that. Flow control is just keep those back to sum. So we don't see the answer at the end, because every time a method is called, it's kept in a side memory on the stack. And then when the final method is called, then we see the answer spun out in reverse order like this. So we'll see something like that. So we're going to see, we pass it sum of 4, and then it's going to wait until it gets to the base case, and then it will give us the answers in order that the stack was populated. So the stack is last in, first out, because this is the last in, and then this is also the first out. So this is the top of the stack. This is the bottom of the stack. So if you think about it as a stack, you would be passing these in as you would say sum of 4 goes on the bottom, sum of 3 goes on top of that, sum of 2 goes on top of that, and then lastly it says what's the sum of 1, and then sum of 1 comes off, sum of 2 comes off, sum of 3 comes off, sum of 4 comes off. So I think I have a blank picture of the set of plates. And so say that this was the method calls. So the bottom one is when it's first called, it's sum of 4. And then the recursive method subtracts 1 from n or from x or from whatever it was. And then we have sum of 3 because it calls itself. So now sum of 3 is the next one, but notice that sum of 4 is at the bottom of the stack. So then 2 minus 1 is 2. So this is sum of 2, and then, which is this one, and then 2 minus 1 is 1, so sum of 1, which is the top. So as soon as the base case is reached, and the base case is set by the programmer, so we could have arbitrarily set the base case as 2, and then 2 would have been the top. But top is usually the lowest number in the base case. So 4 is the bottom, 1 is at the top, so then sum of 1 is the first one that we get back because that's the first one that the compiler can report. So these are like all stuck in memory. And then the compiler just adds them up together. Sum of 1 is 1. Sum of 2 is sum of 1 plus 2 plus 1. So plus 2, so that is 3. Sum of 2 plus 3 is 6, and then sum of 3 plus 4 is 10. So this is the reason why I want to do it like a few different ways, because I put in a few extra print statements in the one that we'll see, but when you first run this, you put in sum of 4, you just see 10. So you wouldn't be very surprised. It's like, oh yeah, sum, it's great, but then if you ever have to write out how the answers actually come out of the compiler, you'd be surprised when you put in the extra print statement. So let's take a look at the extra print statement. Okay, so first I'll run it without the extra print. We'll see that it just comes out as 10. Okay, so here's the thing that you'll want to take a look at here. Okay, so notice up here I have a print statement that says print line sum parentheses within. This is supposed to simulate so that you know this is when such and such method call is happening. Like at first, we pass it a 4, and then this receives a 4. So this is just a message saying sum of 4 is being computed now. But the compiler wouldn't tell you this. They just wrote it in so that you know that sum of 4 is happening. And then down here we see that it's going to print out whatever the value of result is in each step. However, we won't see those done until everything is finished. So let me run this first, and then I'll comment after these two print statements and see what I need. And I'll add one or the other backend alternative so you see that they're just like little reporter print statements so that you can get a glimpse on what's going on inside. Because normally you just see the answer. That's not usually overly helpful to learn. Okay, so first I'll comment on both of these. So if we pass it say if we pass it 100, this should be like, it's like one of those famous math stories. I think it's like 50, it's like 5,000 something or other. But it's all the numbers from 1 to 100 added up consecutively. So you may be familiar with this number because it's like, part of Gauss's little apocryphal history, but all the numbers from 1 to 100 is 50, is 5,050. So now we'll look at 1 to 4, but we'll put in one of the print statements. And if we did it for 5,050, which I guess just I would comment, you can see that there'll be all sorts of steps. But we'll examine one. So we see, so notice that all of the method calls happen first. It'll say sum of 100 all the way down to sum of 1. It won't give you any answers until 1. And then it gives you all the answers spun out. 1, 3, 6, 10, 15, etc. So it waits until the base case is reached, and then it gives you all the answers that it had ready on the stack to give back. So you notice all the way down here, all the way down here. This is how recursive algorithms go. If it were, so let's see, let's go to, if we said from 1 to 4, you might go, 4 plus 3 is 7, but notice that this one does it not that way. It does it in reverse order. Because normally, if we were given 4 and said, subtract 1 from it and give the sum, you'd be like, right, 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10. But then you look at this and it's like, how to do it? It does it because of the stack. So now let's go and change this to, let's change it just to 3, so it's easy to do that. Okay, so let's write this one out. So sum of 3 is called. So sum of 3 comes out as, sum of 3 is the sum of 2 plus, plus 2. Sum of 2 is the sum of 1 plus, it's right here, 2, yeah, right. Sum of 3 would be, okay, so it waits until the base case is reached, and then when the base case is reached, sum of 1 then has a value. So 1 plus sum of 1, which is 1, that was 2. Just give me a second. This is just not easy to do, so I'm admitting it to myself right now, to you. So sum of 1 is clearly 1. Sum of 1 is 1 plus 2 is 3. Oh yeah, that's right. Okay, so so sum of 1 is 1, and then 1 plus 2 is So then the sum of 2, which is now has a value, plus 3 is this. So this is how it will be done. When you do your recursive methods, you want to put in some print statements so that you can see at least the results printed out in the order that they come off the stack. This part you have to get a little handy and put this statement in your method somewhere. But even if we just had this part, the results coming out in the order that the stack prints them out, then you can understand what we're going on. Excuse me. Okay, so we'll do this. We'll do this. We'll do this as the only other one because it'll be enough for us to do as far as writing it out. So factorial. Let's just go to a. But first, let's write this out on the board, and then we'll use this opportunity to write out the math part. So, n prime means n exclamation means n factorial. So this is the equation for factorial. So this is multiplication. So it means multiply the numbers from I to n, where I is 1 here, and this this uppercase pi is the math symbol for multiplication. So this means take 1 and then multiply it by the next one until you reach n, just like we had our sigma meaning addition. So n factorial is done with this, and then this is the way that you'll write out all of your algorithms. You'll have the recursive call on top, and then you have the base case on the bottom with the name of the method and then the curly brace. This is the formulas we will use when we take data structures or other algorithms classes. So this can, for this one, it has to be 1. For our addition, it could be 1 or 0, but 1 is a little more precise because it's the closest you can do it without not completing the algorithm. So the fact that you could do 0, it's not very relevant. But here you can't do 0 because then you would have 0 as the answer from 0 multiplication. So we're going to write out this, because this is normally something you'll have to, like here, maybe I'll do it as like a bonus question or something, but normally in data structures or algorithms, you'll be asked, given f of 5, and f is a recursive algorithm for factorial, give the output from the compiler. And you'll have to produce this. So we'll just write that out and say why the answers are the way they are. However, notice that we have the same exact thing as we had from the addition. The only difference is that instead of adding them, we're multiplying them. Like the first one we had sum of 1 plus 2. Now it's sum of 1 times 2. So it's the same thing. So the fact that it's going to look a little different should not be in any way discomforting. So let's just do this whiteboard. So here we go. So we got n factorial, which we know means n times n minus 1 times 7 until we reach our base case. So we're going to do where n is going to start out as 5, like it was in that example, go down to 1, and then finish. So I'll write out the word facto so it's a little bit more addressable to your subconscious. So we got facto of 5. So our recursive algorithm is going to have a stop point of 1. So we know that, so we'll just say facto of 5 is going to mean, without even knowing all the rest, and based upon how the sum was. If sum was sum equals something, some method name plus some number, what is facto of 5 going to equal, even though we can't compute it yet? 120. No, it's going to remember like sum equal the same method name with a different number in it plus the number.
Oh, 5 times factor of 4.
Yes. Plus. Any guess? That part is hard.
Plus
because
5?
What's that?
Plus 5?
Maybe. Honestly, I don't even know. So that's why I was saying that was the hard part, because that part's easy to see when you start from the bottom, because the bottom is 1. So that part I wasn't going to even pick that. It might be fine. So it is factor 4 plus something. So the next one is factor 4, which is going to be factor 3 plus something. The next one's going to be factor 3 plus factor 2 plus something.
And those are factorials, aren't they?
Well, they're the name of the recursive algorithm that we already saw to do factorial, but it has no meaning in Java. Factor 2 factor 1 plus, and then factor 1. Okay, so here we are, down at the bottom. We know that at the end, factorial of 5, from our normal everyday stuff is 5 times 4 times 3 times 2 times 1. So it's 20 times 3 is 60 times 2 is 120. Times 1 is 1. So it's going to be 120. However, just like we have here where it goes 20, 60, 120, we're going to see our output in a little different manner, because we're going to have not plus, times. So difference here is that it's times. So the only difference for factorial is that it's going to be a plus sign instead of, it's going to be a multiplication sign instead of a plus sign. So if you look back at the algorithm that's on the slides, all you got to do is change the plus to a times, and you get the answer for factorial, because it works out the same. You start out with factor 1, and then you take factor 2, which is factor 1, times, and then the number that we used to add 1 to was a 2, because we did sum of 1 plus 2 was 3. So this is times 2. And then facto 2 times 3. And then facto 3 times 4. And then facto 4 times 4. So facto 1 is simply 1, so 1 times 2 is 2. 2 is the value of the method called facto 2. So facto 2 times 3 is 6. And then the value of facto 3 is number 6. So facto 3 times 4 is facto 3, which is 6 times 4 is 24. So the value of facto 4 is 24 because the value of facto 3 is 6. So facto 3 which is the number 6 times 4 is 24. That's the value of factor 4. So now the value of factor 4, which is 24 times 5, this is 120. So it comes out 2, 6, 24, 120, which is different than we have because it does it from the bottom of the stack. It takes factor 5, which is the bottom of the stack, and then it says that's not the base case, so factor 4, factor 3, factor 2, factor 1. Base case is reached, so it starts peeling the answers off. 1, 2, 6, 24, 120. So this is what's meant by the stack. The base case is the top of the stack because it's the last one that you placed on the stack if you consider the stack of plate, stack of physical plates. So you'll see the call to the base case as the first answer. But if you don't have those extra print statements in, you'll simply see 120. So you wouldn't differentiate it from how you would see it in a for loop or a while loop. But in a for loop or a while loop, you would get the kind of answer we would get, because in a for loop or a while loop, you would say 5 times 5 minus 4, which is 5 times 5 minus 1, which is 20, and then 20 times 3 is 60, and then 60 times 2 is 120. So you would see it in that order, because it would just remove the 1, just like this did, but there's no stack operating inside of the while loop or the for loop. Follow along with that. So let's just look at that in Java. So I'm not even going to bother copying the code in because we want to see that it is just the same as we had here. So notice that this says sum, so it's going to change this to factor, and we'll show that this is exactly the same except for this the sign. So it changes to factor. Change this. So this part is a print statement. So I'm going to put in some F's there just so we see that the compiler has nothing to do with telling us about those method calls of us actually writing it in. Sorry, there's no eraser here today, so it's left to do. So I'm going to just put F's there. I want to just demonstrate that this part is us telling us ourselves that we want to see the method call happening each time it happens. So here will be the let's go with this. So here is the flow of this. So we got up here, we got to call the factor. So factor is called and it's given a number of 5. So when factor is past 5, main is not going to see the light of day until this method is finished doing everything. So facto receives a 5 and then it does all its stuff. But it doesn't return to main because main is not going to be the next thing in the logic loop. It's going to call itself, so it's going to call itself. Main will be returned to once it's over. So factor 5 will come in here. It's going to say FFF because that's what we did. Just we proved to ourselves that this is only our little reporter. If n is 1, so n is not 1, so we don't even bother reading that. So result equals n, which is 5, plus facto, n minus 1. So notice that right there, this isn't even something we see printed out. This is what we were writing. Result equals n, which is 5, plus facto n minus 1. So remember we wrote f of 5 was facto 4 plus 5. That's right there. So the first method call is that, but it's not done because when this calls itself, it's still not 1, so this is at the bottom of the stack. But now n is 4. So 4 plus facto 4 minus 1, which is 3. F of 4 is 4 plus facto 3. So then it calls itself again. It's not 1. So now facto 3 equals 3 plus facto.
2.
No, I don't think I was at 3 yet. So we were at 4, so we're back around to 3. So 3, and it was, yeah, you're right. Thank you. So f of 3 equals 3 plus facto n minus 1, which is facto 2. So f of 3 is 3 plus
But how's it
F of 2.
how's it decrementing though?
right here.
Okay.
That's a function. That's a method call. It's not like we see it printed out. So this is how we see we see all those answers at the end instead of seeing just a 10 or just a 120. But this is also why we see the answers in that weird order, because until it reaches 1, we don't see any of these print statements happen. Because notice in the beginning, we see, this is the weird part about it, we see all these, all of them, but we don't see any of these. And it's like, where'd they go? They're off to the side until f of 5 has a meaning to it. So originally, facto 5 means facto 4 plus 5. But facto 4 doesn't have any value to it until the base case is reached. So all the method calls can be notified that they're done. But until the base case is reached, none of the answers can be computed. So then finally, so f of 3 is 3 plus facto 2. So now 2 goes in, it's still not 1. And then 2 equals 2 plus facto 1, and then go minus 1, and then back around. Now it finally equals 1, resulting with 1. So then it goes in that reverse order, which is why we see the result in the order that we would not imagine it happening if we were to do it from the normal way. If we did 5 times 4 times 3 times 2 times 1, we would not get the answer that the computer does, because the computer computes facto 5 through facto 1 first, takes the answer for facto 1, multiplies it by the answer of facto 2, multiplies the answer of facto 2 times 3, multiplies the answer of facto 3 times 4 until the end. So that's why we get, the last step is 24 times 5 instead of 60 times 2. You get a different answer. Well, not a different answer, a different step. Let's see. So we got, let's make sure everything's good here. So we got facto and minus 1. So here's the only difference between the sum and the factorial recursive function. Plus goes 2 times. So we get method call. So when finally base case is reached, it takes f of 1, which is 1, and then adds it, and then we get this, this. So 24 times 5 is 120 instead of the 2 times 60, which we would likely do ourselves. So all of recursive functions will come out this way, unless you didn't do it where the base case was 0 or 1, but that wouldn't be done, because the base case is 0 or 1. That's how recursive functions are. You could, of course, have made this where it starts out as 1 and you arbitrarily have it stop at 5, but that would be highly unusual, because that's not the thing, I guess, about recursive functions. Well, sorry, recursive methods. Okay, so let's see. So I think let's do a break and then we'll come back and see what we get. I always tell her let me email you this because I didn't post it yet either just because I didn't have it done. So. Do sum and factorial again, which if you really think you got it, great, but like just listen anyway because every time I do this, like I still have to like really focus on it because recursion, if you've got the recursive brain, that's great. But a lot of people don't, so just like go through it again, see if you can write all the function calls out in a pen because even though computer programming, like the output is the issue, with computer science, later you will have to write all the steps. So the important part is to understand how the stack interprets it versus how you would interpret it. And also you can write a loop that does it. After we have everybody post their stuff up for the method call discussion group, I'll put up one where I'll just basically say, convert this into a loop, and then it'll be recursion. So you'll see how the answers come out differently, just like you would get the answers differently as a group.
I walked home so quickly because I was was thinking of shit and I was like, I got pretty far with that.
What was it?
I would say after the chat, but there is no chat right now at the moment.
I might be.
Oh shit.
It's not
I'm gonna let my camera fall again.
make it today.
There you go. Honestly, I'm considering asking for an extension.
I have an extension.
Because tomorrow we're gonna be
Oh shit, 0.1% dropped frame.
I was like,
Frame with the drop of my camera.
been like on the watch for myself this morning because like when I got up I knew it was one of those days. I felt it for like thinking that's right. And so I'll be in office hours 3 to 6.
I have nice, some nice bubblies and wine. Fuck yeah. I'm finishing up my tequila. I know we are still gonna have bubblies and wine, but I'm also going to tequila.
He said, yeah, I do that.
I'm gonna put out tequila.
Okay, so it's 60 frames per second. Oh shit! Almost 6 seconds. Fuck.
I'm gonna have my hand even ask my roommate to roll some joints. She's not said it so loud.
I have to turn my neck like that. And those are the monkey that you know turn its head. Oh. Ooh. Shit, more frames just dropped. Oh, fuck.
Like I got it granted, but I just felt that. It was kind of there, so that's a bit of a question. But I didn't think about going.
Alright, gotta pay attention. Sorry about the dropped frames. Oh, let's copy this. Excuse me.
Oh, I do see the guys. It's the weather forecast for you guys too. Oh yeah, dude. I feel like Trey Boston I'll take Jacob. Jacob. Although, just the whole him and Teddy being that's, I don't know why it's throwing me into such an emotional curveball.
Yeah.
Well, it was very.
Uh-oh.
Yeah.
Chaotic. That's how you guys are placed together.
It's
It wasn't
I mean, it's fine. He was like, he could very much.
Well, I was fun. Yeah, that's good.
We'll see you.
It's nice. All the time. Disclaimer.
Oh yeah, last night I told him that was like some years in front down.
So here's the tea about what happened.
But he already made it.
We'll see you.
You guys all talk. That's why I wear my retainer every night.
Still?
Yes, no.
No, he said at the party, and I'm like, oh yeah, we can do that.
And they're like, no, we paid thousands of dollars to I didn't suffer for
Yeah,
2
I'm
years.
so upset. I'm so hurt.
Did you not?
The next day, I texted him. And it was just like, I was just like, what the fuck? Like, he was so cool in person. And now this. That's why.
We should we be copying this down? Yeah.
It's on stream if you guys like need it. It's on stream like right now.
Thanks.
You're welcome. Whoops.
I'm so angry.
I just decided.
So when I say that I need the sum of n numbers where I'm specifying n,
Um,
I'm so when I want the sum of n numbers and I have n as my user input, one way to go about it would be the normal way to use a for loop, where I'm saying that my I starts from n. Until it's greater than 0, I keep decrementing my I and I keep adding it to sum. An alternative to this would be recursion. Here what I'm saying essentially is my sum is starting from 0 and let's say over here when I called sum for the first time, my n is 5. And inside my function, I'm saying of n minus 1. So I'm passing 4 right. So that's going to, the initial value of sum is going to be 0. So now my sum it's basically working the same way that the for loop is working, just that, so when I say that my value is starting from n and I keep decrementing it, so every time I'm calling the function again, I'm giving it a value lesser than what it's supposed to be. So one thing that's missing from this method is where it should stop. So with the code that I've written right now, it's gonna be stuck in an infinite loop because it's gonna keep calling itself, and there's no stop condition. So we want it to stop as soon as you reach 0 or 1. 1 should be the last number that gets added to it. So if number is equal to 1, so this is going to keep getting called to sum of 1. And now when I say that, since over here my value being passed right now is 1, the last one is 1, and my number is equal to 1, I'm saying sum is equal to 1. After I get a value over here, sum is now 1. I have a value over here. 1 is going to be added to 2, it's going to be added to 3, it's going to be added to 4, and then 5. And that's how I return the value. Sorry, this will not sum, it's the value. For my first function call, when I'm passing the value of 5, my sum has 5 sum of 4. Over here now I have 4 plus whatever this returns. This is gonna call sum of the final value that I will get is 1, which is gonna get added to 2. So similar to how the for loop is working, instead of saying that instead of having a while loop that's going to run for however big the number is, I'm doing recursion, which I think for this problem the complexity would pretty much be the same. But recursion is helpful in cases of trees and stuff because
Of
Yep.
trees?
Tree graphs.
Sugar.
You learn them in script
binary
math.
trees. Recursion is much easier to use there. I wouldn't prefer using recursion for basic math and algorithms because it's unnecessarily complicated in my opinion, but it has its uses. You should just understand how recursion works. Basically, you're just calling the same function, and the only thing you really need is a stop condition. And ultimately, you just keep calling it till you get your value. Is everyone understanding the recursion?
Yes.
Did you guys do exception handling? Is everyone comfortable with exception handling?
You mean try catch? Try catch blocks, you mean? Yes, we've done
Yeah.
that. Because I was wondering, because if you put 0 in, you're gonna get an exception. So are you trying to say we would do a try catch for if someone did put in 0? Okay, okay. I worded that completely wrong. Are you saying that we're going to create a try catch block for when someone does put in 0?
Oh no, I was just asking in general because I didn't do a lavish in this class for try catch.
Okay.
So I've put up an assignment on Zybooks on exception handling. It's a simple one. I don't think I've set a due date for it, but yeah, I just wanted to inform that there's an assignment on exception handling. That's the assignment on exception handling that you guys are supposed to do. I've put up an assignment on exception handling on Zybooks.
Oh really?
You said there was no due date announced yet, right?
So this is our homework?
Yeah.
Okay. Alright. Finally, we use the tech.
Yeah, finally we actually used that. Yeah, I don't think the professor knows how to use Zybooks, so he just told them to.
He said he's gonna get trained. I think at the end of the semester.
Yeah, he asked me to do that.
Wait, so it's in 7.
Yeah, 7.6.
Just that video was.
I'm gonna write this down.
Are you gonna use Zybooks all the time now?
Probably not.
Because it was there. People what happened?
A month and a half left, but
I mean, like, cause there's people doing classes.
Yeah, because it was like, he wasn't having expenses,
So like,
what's the point of
if
that?
there's one
For that
homework
one
assignment,
assignment,
they're gonna get.
So
50 bucks
7.6. I mean, I'm gonna put up assignments whenever I'm not in class. I just tell him that if I'm not coming in, then I'll just put something up for you guys to solve. Okay.
Oh, we can get tomorrow?
Yeah.
Okay. At 4 o'clock, right?
Yeah.
Alright.
See you around.
See ya. I think the Smash Club's there.
Yeah.
Oh, yeah, that's one. Right?
Well, Smash opens at 6 actually.
6.
Yeah, so we have plenty of time. No?
Oh, they open at 6?
Yeah, they open at 6, but they can open the room at 5:30, but usually starts at 6.
Like, I was gonna hold it away, I don't need you no more, like.
Wait, did I tell you I went to the I went to school with him for the Mike Posner's nephew. Yeah. Yeah, his name's Matt Sandberg.
How you know that?
How I know them because at his bar mitzvah he had Mike Posner perform, and I was on it too. He had to perform anyways.
He was I don't know if he was right.
Yeah, he was definitely he was that was Thank you.
What? Got it.
I had a new one.